start with a talk that's a bit more applied, I would say, with respect to those we've seen before. And we're going to look in particular at scene graphs, and how scene graphs can be, first of all, defined and then applied in the context of 3D computer vision. So the talk is divided into 4 parts. We're going to look through some definitions and applications of scene graphs to 3D in particular. And then we're going to look into application of semantic scene graph in images. In particular, we're going to look into those works that represent a starting point for the extension to 3D. Then the third part looks into mostly inference, so how to extract scene graphs from 3D data. And the last part would be around generative model and generation of 3D scenes out of scene graphs. This talk will be intertwined with Fabian, so I'll present the first part, and then it's going to go for the second one, and so on. So what do we mean by scene graph and semantic scene graph? In this case, we've seen before some declinations of graph neural networks and graphs to different types of data. In this case, we're looking into scenes in 2D or 3D. So typically nodes are the objects and semantic components of the scene, and the edges represent the relationship between these objects. So when we look at images, typically this type of relationships can be, for example, actions. For example, holding an object or riding a bike, as in this picture, or proximity, for example, being next to our bike or riding the bike. Support, comparison, and so on and so forth. There is a direct extension of this concept to 3D data, in particular 3D scenes. In this case, the relationship or edges do not really relate too much to actions that one can make with objects, but more to, for example, geometric relationships. Typically, we can say that a certain type of object, like a chair, is supported or lies on the floor, or similarity. For example, if you have 4 chairs that are at the same time type in a living room, we can relate them by saying that they are the same type of shape. It's actually quite interesting to look into the extension to affordances that is somehow similar to the concept of action. So how we can make use of certain objects in our indoor scenes. And this is, let's say, more related to future work at this stage. We won't look into 3D objects and 3D shapes, but for, I think it's worth to mention that since we talk about 3D data in general in this tutorial, that the concept of scene graphs and graphs in general has also been used to model 3D objects and 3D shapes instead of scenes. In this case, the idea is that each node is a semantic component of the shape itself. If you look, for example, at chairs, you can subdivide it into armrests and legs and so forth, and connect them through edges that are either the geometric adjacency or the semantic relationship between the shapes. These methods have been used for different purposes. One of them, I mentioned it here, is structured net, where the idea is that we can interpolate between 2 given shapes, for example, a source point cloud that we can capture with a real sensor, and a target image or target shape that we can get from a database, sorry. And then we can interpolate through the shapes by making use of the graph, underlying graph. And this typically helps to also generate different types of shapes from a given category in a semantically coherent way. So it helps building up generative models. In terms of 3D scene graphs, so going back to the case I mentioned before, why are scene graphs and semantic scene graphs useful? Typically, 3D scenes, let's say, are a very detailed representation of our data, but they tend to have several limitations. One of them is that they're memory extensive. It takes a lot of memory to actually store them, while you can think about graphs as a way to reduce a lot the amounts of memory that you need to represent an image. Another typical reason why you want to make use of semantic scene graphs is that 3D scenes, in terms of 3D their construction, for example, is a very rigid representation, while many applications now in this field are going more towards making use of dynamic scenes, where dynamic doesn't necessarily mean that things move in a scene while they're captured, but also that they move over time. So we want to detect, for example, real changes in a scene that happen over time, for example, hours or days. And in this case, a semantic scene graph is a very powerful representation to model this type of changes. A final advantage is typically that it's a very abstract representation. So we can very simply and in a very abstract way represent the main components of a scene. I will mention here a few applications. On the left-hand side, you can see those related to inference in graph from 3D data. One is, for example, multimodal scene retrieval, where you want to, for example, capture and retrieve a certain scene from a database from a single viewpoint that you can capture with an RGB sensor or a depth sensor. Scene change detection is also an interesting application. As I said before, we want to detect what are the semantic changes in a room simply because there was a person that came into the room and made use of the room by moving things around. So we can just directly use the scene graph to detect these changes rather than applying, for example, differences in terms of voxels or 3D points. And finally, compression, as I said before, because it's abstract, because it's lightweight, we can use scene graphs to simply summarize in a compressed way our 3D scene. On the right-hand side, you can see applications more related to generation and generative models. In this case, one very interesting application is the synthetic data generation. So if you can generate realistic scenes through scene graphs, modifying and manipulating scene graph is a particular easy way to generate a lot of data. And this could be a way, for example, to also bridge the, or say, reduce the scene to real gap in this case. The other one was actually one of the main topics that we discussed yesterday in a workshop on computer vision for the building environment. And there's a strong interest for many applications, for example, in augmented reality, indoor design, work placement to generate layouts. The example I'm showing here is actually not based on a scene graph, but I hope it helps to get an idea of why it's useful to have this type of layouts. For example, we can help designers and work placement experts to generate an initial layout that makes sense, and that then the designer just or the architect just have to, let's say, iterate and refine it, so it can really speed up and improve this type of work. Finally, I'm going to mention this briefly throughout our talk. Also, scene editing and manipulation. We can modify and manipulate our scenes, images, or 3D scenes by manipulating the graph, and this is another very high-level way to apply this type of changes. Very briefly, in terms of scene graph processing, the idea would be for scene graph neural network to kind of rely on very important properties of convolutional neural network. One is the fact that vision in a very local way initially, and then there's a receptive field that going through different layers of the network increases, and then this allows the network to also make use of context. The other one is hierarchical learning, which is typically start with features that are very basic at the beginning and then become more and more abstract and more, let's say, global about the object or shape that, for example, we want to recognize in the image. And finally, there's the parameter sharing, which is, of course, one of the, let's say, major reasons why we're making use of CNNs today. The idea would be, can we try to exploit these properties also for our scene graphs while we apply, for example, a scene graph neural network? Typically, in the case of scene graph neural networks and inference on scenes, the declination of the graph neural networks that's being used relies on a triplet-based approach. So we take our graph, we split it up into triplets, where typically you have two nodes and one edge of relationship. And this can include, of course, the same node, so they kind of get duplicated. And then the first step is simply a propagation step, where we take the initial features of each node, and then we propagate it through an MLP that learns another feature for each of these triplets. Then there's an aggregation step, where typically you apply a set of concatenation and pooling, so that, as you can see here, the feature related to the same node is aggregated together. This is some sort of message passing that, if we iterate on top of that, can allow basically information to be shared across multiple nodes in the network, even potentially very far away. And the third step is an update step, where there's another MLP that learns from this new set of aggregated features and provides a new one that then is used to iteratively go through a set of layers of the network. So in this case, you can see that, first of all, we can apply a message passing that can involve entire nodes of the network. And the more we go through these layers, the more we increase somehow the, let's say, equivalent receptive field of the network. And the other advantage is, as we were saying before, parameter sharing. In this case, we really have the same MLPs that are kind of shared throughout the layers. And this makes a good use, let's say, of our weights and our memory. So these are quite powerful tools. And the second part of the talk will be related to images, how scene graphs have been used in images, and in particular, those applications that inspired the then application to 3D data. And for this,
Yeah, okay, so as Frederick already mentioned, while we are focusing here on 3D scene graphs for 3D data, we want to start with images because most of the works that we're going to see later are inspired by these works for images. And we first let's take a look into what can we do with scene graphs. So one thing is we can basically just start inferring scene graphs. So we start from an image, and the goal is that we take this input image and we want to generate the respective scene graph for it. Thanks. So we have this RGB image and we want to get to a scene graph that describes the scene that we have seen. In this work, what they're doing is they predict the scene graph using an RNN, and then they do message passing, as described before, to propagate the features through the image, through the graph, and then at the end do the prediction on on the object class. And also they also predict bounding box and say that if you do classification using such scene graph approach and you do message passing, also classification of the object detector improves using these features. So you start simply with taking an image and you run it through a region proposal network to detect all the objects that are currently in the scene. And then you basically build a graph by always looking at two pairs of objects. And so you basically get the features for each object. And you also get the features for both objects by taking the union of the bounding boxes. And then you have this RNN that produces a state that describes the current graph, the current node and the edge. And here what they do is they split it in basically two graphs, one for the node and one for the edge. They do message passing as described before, aggregate the features, and then keep repeatedly doing this to get high-level features until they run the inference for object detection, like the bounding box, as you can see on the top, and also for the graph. Here are a few examples. So you see the scene graph for the given image, and as you can see, overall it seems to work very well. Like the train is in the scene, and the connections or the graph makes sense. Next, we can infer the graph, but the question is, can we also get the image from the graph? And so when we look at this here, we have this graph with two sheets, and they are on some grass. And from there, what we want to get is the respective image. And this work builds again on top of these GCNs to process this input graphs, and then it runs a bunch of forward passes and predicts a layout, which is then turned into the image. And they use some adversarial training to get highly realistic outputs, or quite good outputs, I would say. So we start from this scene graph. For each one, we embed it into some feature vector, and then we run our graph to predict the layout and the mask. So we predict the bounding box for each node, and a feature, and also the mask where the object will be. And then we run a bunch of forward passes with the CNN to get the respective image for this given graph. And you can see a few qualitative results again. In the top, you see the graph with, I think it's again two sheets on some grass. And then in the middle, you see the layout that the network produced with the masks and the features. And at the end, you see the final output image. In the paper, they also described that it works better than, for instance, models that are based on text in respecting the overall content of the 3D scene. So it seems like the text models, they often skip parts of the object that were described, while here they are better reflected. Of course, with now with these new diffusion models, it might look a little bit different. And finally, we can now get the scene graph. We can also get the image for a scene graph, but the question is, can we also apply modifications, basically? Can we use a scene graph to make changes to the initial image? And that's exactly what they did here. So as you can see here, you have this image, input image in the graph, and we now switch the node or the attribute here from writing to next to, and on the right we see the respective output image, which now the woman is standing next to the horse. And the problem here is that there is not really data for this task. So there's not really data where you have a scene graph and then you have the corresponding output image where the change has been applied, but everything else stays the same. So how they trained this was in a more like an autoencoder fashion. So they had the input image, they used some graph predictor or ground truth graph in this case to get an edge embedding in the node features. And then they used a similar approach than what we have seen before to go back from the graph to the image. And doing training, they kept also dropping features for the node, as well as for the like for the bounding box, as well as for the visual representation, and let the network basically fill those in. And when you train that way in an autoencoded fashion, the network is later on able to basically do changes if required. So if you done change like the content of the node and we mask this out, we get the new image with the change. And here are a few examples for this. So they did object replacement, like changing the sheep to elephant. Then also object removal, so simply dropping a node from the graph, or also changing the relationship. So here we see again this example from right next to, but also like sitting to standing can be done that way. Okay. With that, I pass it back to Federico.
Okay, so we've seen how the, let's say, more image-based field has been quite active in trying to use scene graphs for both generating a scene graph on an image and vice versa, which means given a scene graph, generate an image in a, let's say, realistic way. So we can do, for example, image manipulation. So these concepts are actually more recently inspired a lot the 3D community in order to try to apply this on 3D data, in particular 3D scene, as we've seen before. The extension is conceptually very simple. As we said before, the concept of scene graph can be easily changed or translated from images to 3D scenes. In the indoor case, typically, as we said before, objects and relationship, geometric or semantic relationships, but everything else kind of stays the same, and we can use again the GCN approaches that we described in order to make inference on 3D data. So I'm gonna talk in this part in particular about the inference part, and Fabi will finally conclude with the generative part. One of the first works is actually related to also contribute to a data set. So the community, of course, requires data sets where you have scene graph annotations. This is what was proposed with this 3D SSG work. In this case, the authors took a previously proposed data set, which include 3D scenes with real changes over time, semantically labeled, and applied annotation in terms of nodes and edges. So now you can have a variety of 3D scenes where you have annotations in terms of the graph, and also scenes that change over time with the same graph, basically graph annotations are applied. This is particularly useful, for example, for the scene change application that I mentioned before. The inference algorithm itself is pretty simple. The idea is to take 3D bounding boxes around each of the semantically labeled objects, and then apply a simple 3D feature encoder. In this case, it was simply a point net, and this represents the initial feature that we associate to each of our nodes in the graph. For the edges or relationships instead, we do something similar, just that we use a 3D bounding box that encloses both objects for which we want to compute the relationship. But the approach is the same. We compute the point net, and then this is the initial feature associated with that type of edge. Then we run our GCN, as explained before, and this ends up with, let's say, refined and improved labels for both the nodes as well as the relationship. These are some initial results that were proposed. Now, the nice thing for the community is that there's a data set, there's a training set, there's a test set, and there's a set of metrics that can be used to compare. And there's already a few more recent works that have been used that are now relying on this framework and test bed in order to compare and improve the results. In this work, they also show, let's say, some of the applications I mentioned before, for example, the multimodal or 2D to 3D scene retrieval. So we can use an input 2D image or an input depth map in order to retrieve a scene from a set of 3D scene database. I won't really go into the details for reasons of time, but these are just some results where particular metrics specific for this type of scene graph inference, such as, for example, the Jaccard index, have been used to make the comparison, both in the 2D to 3D and in 3D to 3D case. Another application that's somehow mentioned in this work is the scene change detection. As I said before, these annotations are based on a database where there are real changes across time for the same scene. So if you have the possibility to extract a scene graph in both cases, so before and after the changes, we can directly leverage the changes in the scene graph to quickly detect those semantic components that change, for example, because the node label changed, for example, an object that got removed from the scene, or the relationship. In this case, you can see, for example, a pillow that got moved away and closer to a different node, or for example, the chair. The dataset is available, and you're welcome to have a look at that. So we've seen so far how we can infer 3D scene graphs from a set of 3D reconstructions. This is, of course, something that requires someone to first go into the scene and scan our scene with some sort of sensor. This is sometimes a little bit cumbersome. So one of the next steps that was interesting to investigate is whether we can do this incrementally in real time from a sequence of data. In this case, we rely on a SLAM pipeline that provides, let's say, that relies on an RGBD set of frames. And the idea is that while we use the SLAM approach in order to reconstruct our scene and extract the semantic components, we want to also incrementally extract the scene graph. You can skip this slide. This is just a presentation of the work that was presented last year at CVPR. To briefly introduce the method, first we incrementally build a 3D geometric segmentation from our RGBD sequence. This is frame by frame. And then for each of these geometric components, we associate a set of nodes, and we build up a partial first version of our graph. In this case, we also use the same encoding for the features. So we use PointNet for both the edges and the nodes. Then we apply the GNN or GCN, exactly as we mentioned before. In this case, of course, it's very important that this can run particularly fast, because we want to run this for every frame in a real-time manner. The difference now with respect to what we've seen before is that this partial graph needs to be fused into a global 3D scene graph very quickly and very effectively. So you have to imagine that every frame in the sequence provided with a partial graph, this is very partial because it's just a frame, and how to basically fuse this together. One possibility, or one, let's say, suggestion that comes from this work is to also include labels such as, for example, part of. Since you're going to look at objects from different viewpoints, you're going to have multiple frames where the object is only partial. So part of basically tells the network that there's going to be other viewpoints where the same object will be seen, and then you can aggregate it together in the same object. This is just another qualitative result of this approach, where you can see a sequence, RGBD sequence, and the incremental reconstruction that describes both the geometry of the scene, the semantic segmentation, as well as the semantic scene graph. And with this, I'll pass it over to Fabian for the fourth and last part of the tutorial.
Okay, so now we have seen also how to get the scene graph from a 3D scene. So again, the question is, can we also generate the corresponding 3D scene from a graph here? And so what I want to do here is we want to be able to, at least in this work, the authors wanted to be able to synthesize new scenes. They wanted also to be able to do just general completion. So we add a new object to the current scene or suggest new objects. So the input here was a floor plan and an empty or partial room, and then they propagate this room with these new objects. And they did not really use scene graphs, but it's still interesting to see. But they used an unordered set of objects, which they then added to the scene here. And this was done in an autoregressive form using a transformer, as we'll see in the next slide. So starting from a scene, which with a scene layout and M objects, like you can see here in blue, object 1 and so on, and in yellow, the scene layout. Features are extracting using a ResNet here, and also from the structure encoder for all the objects, like the class, installation, rotation, and also scale properties. And then we have for each object a feature and also a query, which we feed to the transformer to predict obtain some more high-level features. And then with the trainable query, we then infer the next object that we want to add to the scene, and they do it in auto-recursive fashion. So they first predict the class of what object do we add, then where do we put it, like the position, location, because it should also fit to the current scene. So they do it in a step-by-step fashion. Here's some qualitative results on when they trained it with this 3D front. So the output, so the method was really able to infer very nice 3D scenes. The thing is that we have no control over this. Basically, we cannot really describe it. It just adds the next object to the scene in a way that makes, of course, sense. But it would be nice to, we were thinking it would be nice to also be able to control this. So in this work, what they did is they started to get it from a 3D scene graph, and they wanted to predict the layout or basically the whole 3D scene for image generation purposes. So they basically, what they did, they went from this graph to the layout, and then they do retrieval to get all the objects. They actually also did some refinement using differentiable rendering, and then they rendered more or less the output image. They started by, you start from a graph, the scene graph, and for each node, you basically feed the properties of the layout. So in this case, the boxes with the width, height, length, its position, and also its size. And then they use the variational graph autoencoder to embed it in a latent space, and then reconstruct it and having some reconstruction loss at the end. And from this, they could use from the distribution, from the Gaussian distribution that they obtained at the end, they could basically sample new scenes by sampling sampling each node from this distribution and decoding it into the final layout. And as I said, then they use the diagonal of the bounding box to retrieve the objects for this scene. And here we have some qualitative comparison with this paper from Johnson for the image generation. So you can see that given that they use this 3D layout or this 3D scene as an intermediate step, they get much more nicer images at the end, and than the Johnson paper where the objects are very blurry and sometimes you don't see the borders. The problem here is that this is not end-to-end trainable. So we were wondering, can we make this all end-to-end trainable in a way that can we go from a graph directly to the final 3D scene? And of course, it should again follow the constraints of the graph. And in this case, like in this image work before, we also wanted to be able to apply modification or changes to the graph, and then the scene updates accordingly. So we start basically with a very similar approach from variational autoencoder for this graph, but we add also features for the shape of the object to the scene. And in this case, we either use features from AtlasNet or from DeepSDF and enrich with this our scene graph. And then we ran both through an encoder and then to some shared encoder to get this shared length and embedding. And this we could then decode again into the shapes and the layouts to use the final scene. And we had also this manipulator network, which directly works on the latent codes. So if, for instance, if you want to add an object, we just added a new node in the latent graph, sampled some noise to make to allow basically always different scenes, and then we ran it through the decoder to apply these changes. The thing is that for this task, unfortunately, it's hard to evaluate it. So the way we did it was that we used the method that was presented before for scene graph generation as a proxy to evaluate it. So we first took the scene graph, then we predicted constructed the respective scene, and ran again the scene graph prediction network to get the scene graph again from the scene, and then compared it with the initial input. And we could see that we could achieve better results using this shared embedding between shape and layout than just simply doing one network for the whole scene as the 3D SNN method. And what was also very interesting is that our model was even able to consider the context of the scene. So here, when I had a chair next to a desk, it always gave me an office chair most of the times. But when I, for instance, tap or remove this connection or said it's another table, it gave me just a normal chair. So the model was really able to understand the context. And here are a few more qualitative results. So the first one was with DBAS-DF. So we see the scene graph and the generated scene. And also these changes that, for instance, in the first one, we added a pillow. In the second one, we changed the size of the chairs. So now the room becomes smaller. And then we moved the table, the TV to the side, or also added a cabinet to the bathroom. And with this, I want to already conclude and a little bit talk about future directions. So the scene graphs are, of course, also useful in other ways when we are dealing with scenes. So what I wanted to very briefly mention is this holistic 3D scene understanding. So either trying to do 3D object detection, but for this to basically use the scene graph to refine. So you get the initial 3D object detections, the bounding boxes, you feed it to a scene graph, and then you use it to refine the obtained 3D bounding boxes by making sure that there's no intersection, there's no violations of physics and other properties. And they also extended, here's some qualitative results then, but they also extended this at the end to panoramic 3D scenes, and it also works quite impressively. With this, I'm actually already finishing. It's what we saw today was still like very early first steps towards 3D scene graphs in 3D vision. But now that we slowly getting data sets, we're slowly getting first approaches. I think it's a very nice moment to hop on the train and basically come up with new methods and evaluate it. And I think there's a lot of potential in the future. Thanks.